it, and I'm going to share my screen. Now, I'm not going to answer anything more about the quiz, okay? Like I said, everything will be auto-graded. Quiz is auto-graded. There's no choice. Okay, I hope my screen is visible now. Yeah. Somebody, please mute your mics if you're not talking.
Confusion about it that in NumPy arrays, when we create an array, we get numbers in the form
I
like
can't hear you.
1 point and 0 point.
I'm not able to hear you, Smigda. What did you ask? Try speaking closer to the microphone. Do you have a question, or shall I start with the lecture today? Okay, let me start with the lecture. If you have a question, you interrupt me in between, okay? Yeah, I hope. So just for people who came in late, we are planning to have another quiz, the quiz next Tuesday. Okay, that is, today is what? Today is 6th, right? So maybe around 20th. I'll let you know. Maybe a quiz week. But I'll confirm everything on email. Okay, so we'll study a little bit of probability
individual
today.
weightage.
Each quiz is 10%, 10. Like we thought of having 2 quizzes, 20, but each 20 and now I made it into 2 of 10. So 10. Quiz 1 will be quiz 1, quiz A, and quiz 1B. Quiz 2 will be quiz 2A, quiz 2B. 10. End sem is 30. Fine.
And this answer the syllabus is full.
Syllabus?
Yes, sir. What about syllabus?
For what?
For a next quiz.
No, everything. It starts, always we start from the beginning. Okay, because in something like Python, you cannot say topics from previous things will not come. So it is a non-decreasing function. Like your CDF, cumulative probability density function, probability distribution function. So whatever is covered, anything can come in the quiz. So please be ready. There's no syllabuses, everything up to then.
So n-1 or n-2 नहीं हो रहा क्या? और सिर्फ
I can't say that now. I can't say that now. Okay, we'll try, but I can't guarantee.
Okay, sir.
Okay. Fine. So like I said, it's maybe a little dry, but try to get the idea what I'm trying to say. Okay. So now we are interested in things which are which depend on deterministic things. Are some things which you can exactly repeat again and again, and no matter how many times you repeat, you get the same outcome. For example, x is a deterministic function, because every time for whatever value of x you give, sin x will always give you the same value. But whenever there are experiments which depend on chance, there is always some amount of randomness available. So before getting into this tossing coin and all that, so let me ask you one. Okay, now you have been studying probability for some time. Now suppose now all of you have cell phones. Now I pick 2 of you, and I make the first person. So suppose there is you're looking at some scenery. Okay, there is some lake or something in front of you, or let's say you take a very static scene. Lake means there is water moving and all that. So let's take a very, very static scene. There is, let's say, just a blank wall with some painting on it. Okay, now I call you both have exactly the same phone, the same model of the same phone, maybe iPhone 11, both of you. Can you hear me? Okay. Yeah. So I pick up two people.
Yes, sir.
Yes, sir,
I
we can hear you.
I pick up two people and make you stand in front of a wall which has got some painting on it, and I give you both an iPhone 11. Okay. So the first person I give you iPhone 1, the second person I give you iPhone 2. There are two iPhones. Then I ask you to go stand in one exactly the same place, exactly the same settings, nothing has to be changed. Hold the phone exactly in the same way and click a picture of that wall in front of you. So the first person, let me remember some name, Snigdha. Okay, she was saying something. So I ask Snigdha to take a photo. So she takes the photo. Then let's say who else? Prashun. Okay, so I ask, after she takes the photo, I ask Prashun to come, give him his phone, the second phone. I ask him to use exactly the same setting, exactly the same position of the hands, and then take the same photo of the same scene. And now if I compare, now if I use something like Python or something, I load those images from the phone into computer, and then I subtract those two. Suppose the first photo is x1, the second photo is x2. Both of them are basically two matrices. So if I do x1 minus x2, what will I get? We get 0. Did you understand what I said?
Yes, sir.
Yes, sir.
Yeah, exactly same scene, same type, same model of phone, same
Zero,
location, same setting, same position of hands. Everything is the same. Static scene in front of you. Two photographs. X1 minus x2. What will you get? Will you get a 0?
Yes, sir. It should be 0.
Any other answers?
If they are exactly same, then they will be 0. And if not, there will
I
be the
couldn't hear.
difference of them.
Can you repeat?
Sir,
Can you repeat?
if the two photos are exactly the same, then it will be 0. Else the difference of them will become.
No. So I told you how the photos are being captured. Right. I just explained the experiment which I just conducted. Given that experiment, the two outcomes are x1 and x2. Now, will x1 minus x2 be 0? That is the question.
Sir, it may be very near to 0, but we cannot surely say that it will be 0 only.
Sir, can you please
Why?
repeat the
Why?
experiment?
The experiment is there are two iPhones, exactly same identical iPhone models. iPhone 11 or something. Okay. By using those two, I asked two people to take a photo of the static scene in front of you. Maybe just a painting on a wall. So nothing is moving. The scene does not change. Whatever the camera sees is exactly the same. So the first person takes a photo. That photo is x1. Second person takes a photo. That photo is x2. I use Python, load x1 and x2, and I do x1 minus x2. Will I get 0 metrics or not?
No, sir.
No, sir.
Why?
There will be some difference.
Because the coordinates of the photographers would not be same.
Exactly. I'm telling you everything is the same. I'm asking that person to stand in front of the exactly same angle
Yes, sir, it will be 0,
position,
sir.
same angle, same.
0,
Any
sir.
other
0.
answers?
Sir, but
No, sir.
the
No,
time
sir.
would be different, sir.
Except 0, any other thing between 0 and 1.
Sir, it is practically impossible, but if you consider the ideal scenario that each of the pixels are at the exact same position, then you
The
can
time
get
coordinate
a
would not be same
blank
for
image.
both.
So let us take
Yes,
an
sir.
even more. Let us take an even more. I said the scene is static, so nothing is changing. So it's a very controlled experiment. Nothing's changing. Suppose if you don't want an outdoor scene, you can go inside some studio where everything is fixed, nothing is moving. So let's take a even more extreme case. You use the same phone, the same identical. I mean, not two separate instances of the same model. I'm giving you the same phone. The first person. So to remove any kind of randomness, what I will use some robot or something which is fixed, or some stand which is fixed onto a or something, put phone there. So everything is rigid. You cannot change anything. Okay. So the phone is put there. At time t1, I remotely tell the phone to take a photo. I put it on timer or something. So at let's say at 9:14:06, first photo is taken. Then at 9:14:20, the second photo is taken. Nothing is moving. Exactly same room. The phone is fixed. There is no movement. Same phone, same scene. Two photographs, x1, x2. Again, if I do x1 minus x2, will I get 0?
Yes.
Yes, sir.
Well, actually, the answer is no. You will never get 0 because any sensed signal, anything, whatever you are able to sense with a sensor, like so in the phone you have a CCD sensor, a charge coupled device, which reacts to the light falling on it. So every sensor has got some amount of randomness. There is some thermal noise. The atoms, the molecules inside are constantly changing, are constantly. There is all some thermal noise. You can never ever get 0. You are limited by the precision of your of how you represent the data. For example, if you're doing it in a 64-bit word length, all the pixels will be represented as some floating point number. It has finite precision. So within a finite precision, maybe x1 minus x2, if you are taking care of 64-bit precision, maybe x1 minus x2 in some cases might give you 0, but that also is highly unlikely. The true value of the pixel, first of all, you will never be able to represent because you have a finite word length. But even if you are able to represent, you suppose even if you have infinite precision in your computer, still if you do x1 minus x2, you will not get 0 because there is always some random fluctuation, some thermal noise. It may be very, very small. Your sensor may not be capable enough to capture such small variations. But suppose you have a very high, extremely sensitive sensor, you will never get 0 because every signal which you sense, any transducer you use, always introduce some randomness. So like I said, based on the application, based on the precision, based on the sensitivity and all that, the randomness may be very small, but it is never 0. So x1 minus x2 will never be 0. Okay, so that is the case. Always any sensed signal will always have some uncertainty. Any measurement, whatever kind of measurement you do, some uncertainty will be there. I mean, if you are sensing, I'm talking about sensing of physical signals. If you are generating your own data, for example, if you're doing some random number generation or something like that, then by controlling the random number generator, controlling the pseudo random number, how you create the pseudo random number, maybe yes, it is possible to create exactly two sets of data such that x1 minus x2 is equal to 0. But whenever you sense a real world signal using some sensor, there is always randomness. You can never make it 0. Okay, so probability is there always. There must be some way to measure that randomness, and probability theory gives you the tools to do that. Fine. So that was a practical example. But so to develop the model more easily, we need to come up with more simpler models or simpler experiments. So let us look at experiments which depend on chance, and such a experiment is known as a random experiment. Okay. So an experiment here means anything. I mean, like, so it is just a very abstract term. It can be used to describe any process that will produce some outcome, and outcome is a observation. Okay. And of course, these experiments are random in the sense we are not able to exactly predict what is the outcome each time. So then there is a sample space, which you already know, I think, which is a set of all outcomes, and an event. Oh, I think that's a typo. I mean, event is actually a subset of the subset. Okay, and so it's not a typo. An event is a set of outcomes. Like sample space is the space of all possible outcomes. If you take a subset of that, or if you take a smaller set from that sample space, you get a event. Okay. Now this is the standard example. So suppose two coins are tossed, and if the experiment is that, and the outcome is so you toss two coins and note what is the head which comes up. I mean, what is the face that comes up, whether it is a head or a tail. So I've listed out the space, which are all four combinations, and I've listed down a subset of the sample space, which is here actually A is an event that first coin lands on heads, so that's HH and HE. B is the event that the second coin lands on tails, so that is this I'm sure you know what it is. And once you have the representation in terms of sets, you can perform set operations. So A intersection B is HT, whatever is common, and this pertains to the event that the first coin landed on heads and the second landed on tails. Fine. So these are standard things which I think it might have been covered in DS2. Okay, so let's look at some examples. Another example, urn and ball. Like this is also a standard example. Suppose there is an urn, like a big container with 3 balls marked 0, 1, and 2. The urn is shaken, a ball is picked, and the number is noted. That is a random experiment. Okay. What is the outcome of this experiment? The outcome of the experiment is going to be a number from this set S. So this is my sample space. So each time you pick up one ball from the urn, and the ball is replaced actually. So that means the outcome will be either one of these numbers, any one of these numbers, 0, 1, 2, right? So one typical trial which shown here is like this. So these are the various trials. So the experiment is repeated here 100 times, and each time you can see that one of these outcomes come. So either it is 0, 1, or 2. So you can see, since it is an experiment, you really cannot predict what will be the outcome, right? So that is what is shown here. But it is not completely random. The experiments to be for it to be useful to you, you need to exhibit something which is some regularity in the randomness. So that is termed as statistical regularity, and that essentially means that the average obtained, if you repeat it multiple times, long number of times, you will yield the same value. So that is, let me see if I have it here. Okay, so let us repeat this experiment n times under identical conditions, and we have some notation here. Number of times ball k appears, I write it as nkfn, where n is the total number of trials. Small n is the total number of trials. So nk here means the number of times k has appeared. K is either 0, 1, or 2 in this particular experiment. Relative frequency, we have studied it when we studied histograms, and that is nothing but the number of times k has occurred by the total number. And what I mean by statistical regularity is that as n tends to infinity, as the number of trials increase larger and larger, the relative frequency will approach a constant, and that constant is known as the probability of outcome k. Okay, so with respect to this random experiment, we are looking at relative frequency. So here it essentially what it is meaning is the probability in the limit is essentially the number of favorable outcomes divided by total number of outcomes. Right? This is the standard simple definition of probability, which is known as the frequentist definition of probability. This is the intuitive way. Total number of favorable outcomes divided by total number of outcomes. Right? So this is, remember this term. This is the frequentist definition of probability. So that is what is shown in these. So if you make the number of trials more and more, here it is 50, here it is 500, you can see that for this urn and ball experiment, it approaches the value 1 by 3. So that is expected because there are 3 balls and all the 3 are equally likely to occur. Fine. But okay, there are some details here. I'll skip the moment. Let me come to the axiomatic approach. See, the frequentist approach, what I just said, number of favorable outcomes by total number of outcomes, is not enough. That definition of probability is not enough. We need another definition of probability called the axiomatic approach to probability. What is this probability? What is this definition? Here, the problem is that the problem with the frequentist approach is that we don't know how to commit, Okay, we don't. I mean, so mathematically we don't know in what sense are we talking about the limit. Then we may not be. We will not be able to perform an experiment in number of times. So we will always whatever pk, whatever we get as an estimate is always going to be an estimate, because we can never perform an experiment infinite number of times. And some experiments be repeated. For example, if an experiment involves you to destroy a bottle and see what is inside, then once you destroy the bottle, you will not be able to repeat it again. No? Some experiments you cannot repeat. So definitely the frequency representation, the frequentist definition of probability is not sufficient. So that is why we go in for the axiomatic approach. In axiomatic approach, probability is defined as a set of axioms. It is independent of the applications, and we must also be able to interpret it in the frequentist way. That is, it is the relative frequency of an event. Probability is related to the relative frequency of an event. So we must be able to have another definition, and that is what is done in the axiomatic approach. So so that means we will have to define some random experiment. We will have to define a particular sample space. We have to define events, and each has to be assigned probability PA. Okay, so we are not telling how to do this, but if you have these conditions, then you can go ahead with the axiomatic approach of probability. So probability is defined in a few axioms. So these are some of the axioms. So the value of probability should be between 0 and 1. Probability of sample space is 1. And if A and B are two events which cannot occur simultaneously, then this is the sum rule. So probability of A or B is equal to probability of A plus probability of B. So that is, if A and B are mutually exclusive, then probability of A or B is probability of A plus probability of B. So these are the fundamental axioms of probability. There's one more axiom which deals with conditional probability, that we will come to it later. But so the whole point of today's lecture is that there are two definitions of probability. One is the frequentist approach, which shows number of favorable outcomes by the total number of outcomes. The second is axiomatic approach. So frequentist approach is limited in its application. So we, for practical uses of probability, we always go for the axiomatic approach. So we define probability by a set of axioms. Okay, and the axioms don't tell you how to do this, but it tells you that if you have these things in this fashion, then you can apply, you can build on top of models, can be built on top of this. Fine, so I'll stop here. Do you have any questions? Okay, if there are no questions, I'll stop because quiz will start at 9:30. Okay, so please log into your class marker and I'll sharing. I'm stopping the recording.